So why Einstein is so great? Yeah, 100 years ago, he already discovered something which nobody understands him, right? And then 100 years later, we built a telescope, which is in the US at this moment called the LIGO. And that telescope still works to date. And that machine or that equipment have discovered the waves from space. And that evidence, that physical evidence, proves that Einstein was right. So his brain was able to develop something years ahead, and that's why that theory still inspires us today. So why, that's one of the reasons why I named this new telescope Einstein. And second is, this new thing we're going to build will be far better than this LIGO that is in the US currently. And for our region, most important is we will be one of the 2 locations be selected. And that decision will be made by the EU by the end of next year or even onwards, but still being a part of the, let's say, the big effort at national level, that a lot of funds have been granted by the Minister of Science, Minister of Business from the Netherlands, and our project also financed by them. And the goal is not only to understand the wave from space, what they will tell us, but also the purpose of the whole project is to inspire more companies in the region. So the technology that we can use for this probably can be used for a lot of other areas, because this whole telescope equipment is not only physical things, that they will inspire people in materials, inspire people building equipments that can be applied for other business, but also software side, which means a lot of data, information, analytic skills will be used to apply, because if we get those signals from the space, still we need to understand how does it work and what that tells us. So our work stream focus on the AI techniques. So there are Professor Chris, he's from University of Utrecht. He leads our work stream, and he will tell you about very general idea what is gravitational waves and what we've been doing with that. And we have also our project team members, and that's Melissa and Tom, and they've been working for years on this already. And they will tell a bit more in depth what we can apply with our current knowledge to understand this. So quickly, today's agenda. So Professor Dr. Chris van den Broek will tell you a nice story. Hopefully that inspires us as well as you guys. And then later followed by Melissa, and sorry, Stefano, he's supposed to come today, but he's sick. So Melissa is a colleague of him, and she will give the talk. And Tom will talk about also another techniques that we use for it. And the last, there'll be enough time for you to discuss the content and the questions, and have a nice drink to finish the day. Okay, so welcome, Professor Chris.
Thank you. Okay, so all right, I'm going to tell you a little bit about the background before we delve into the very technical stuff, or well, it won't be that technical, as you will see. But anyway, gravitational waves, what are they good for, and what is going to happen in the future, also maybe in this region, that is indeed Einstein Telescope. So now, first, to understand gravitational waves, we have to go back quite a bit in time to 1915, when Albert Einstein formulated what is called his theory of general relativity. Now, by the way, this is Einstein around that time. So we are used to seeing white hair, shock of white hair, right? But around that time, he regularly went to the hairdresser. Still apparently. But okay, so he came up with this theory of general relativity. And what kind of theory is this? It is actually a theory of gravity. And in that theory, there is no gravitational force, like you may have seen in high school. Newton thought of gravity as a force. In the case of Einstein, it's not a force. If this is the sun, this is a cartoon picture, of course, then the sun causes space-time curvature in its vicinity. And now this little ball here is meant to be the Earth. Now, in Einstein's theory, the reason why the Earth stays in orbit around the sun is not that the sun exerts a force. No, it is that the sun curves space-time, and the Earth is compelled to follow that space-time curvature. So that is roughly how it works in Einstein's theory of general relativity. Okay, so the sun curves space-time in its vicinity, but now there are other types of stars. So, for instance, white dwarfs. And a white dwarf is typically a star with about the mass of the same mass as the sun, or maybe even heavier. But all that matter is compressed into a much smaller volume. A typical white dwarf is about the size of the planet Earth. Now that's very compact for a star, right? That's so one solar mass worth of material compressed into the size of the Earth. As a consequence, this object being much more compact, the space-time curvature in its vicinity will be much higher. Space-time will be much more curved in the vicinity of the white dwarf instead of by comparison with the sun. There are even more compact stars. So if you press on a white dwarf, you get something that is even more compact. And that is called a neutron star. As the name suggests, neutron stars mostly consist of neutrons. And that is because the pressure inside the star is so high that electrons are pushed into protons to form neutrons and neutrinos. But anyway, and when the pressure is high enough, then you end up with almost only neutrons. Now, a neutron star, again, is typically about the mass of the sun. In fact, a typical neutron star is between 1 and 2.5 solar mass, so even more massive than the sun. But it is even smaller than a white dwarf, because a typical neutron star has a radius of only 10 kilometers. But that's the size of a city. Okay, so imagine the entire mass of the sun compressed into something the size of Los Angeles. If you press even more, then matter can't take it anymore, and it's going to collapse to a point, and it's going to form what is called a black hole. And a black hole is a region of space-time where the space-time curvature is so strong that nothing can escape from that region, not even light. And then black holes come in all sorts of, can in principle have all sorts of masses. And then there's a relationship between their radius and their mass, which was figured out by actually somebody who, somebody figured that out 1 year after Einstein came up with his general relativity. Karl Schwarzschild came up with the idea of a black hole. Now, suppose we take these very compact objects, neutron stars or black holes, and we put them in orbit around each other. Then what is going to happen? Well, each of those two objects, of course, causes itself very strong space-time curvature. It's a very compact object. But moreover, as the two objects move around each other, the space-time curvature constantly needs to readjust itself because it sort of needs to track the two objects, right? But at the same time, what happens then is ripples in the curvature of space-time that spread out at the speed of light, and those are the gravitational waves. But that sounds kind of abstract, right? So ripples in the curvature of space-time, can we visualize this? Can we have an idea of what that might mean? Well, suppose that far enough from my binary neutron star here, suppose that I place a ring of particles. So I have a ring of particles, which if there's no gravitational wave, then it forms a circle, a nice perfect circle. And I place my ring of particles far away from the influence of the Earth or the sun and so on, so that they can really only be affected by gravitational waves. Well, if a gravitational wave comes by, and in this case, you have to imagine the gravitational wave coming straight out of the screen, perpendicular and towards you, then what the gravitational wave does to space is that it stretches space in one direction and compresses it in the other, and then the other way around again. And if you have a ring of test particles, as we call them, then this is what is going to happen to that ring, right? So it gets stretched in one direction, compressed in the other. Half a period later, it is the other way around. So that is what gravitational waves do to matter. And it actually also suggests a way of detecting gravitational waves. Because you can just imagine having such a ring of particles hanging somewhere in space, and you just wait until you see a wobbling like this, and then probably you've detected a gravitational wave. Now, unfortunately, in practice, that turns out to be too difficult a thing to do. You hang a ring somewhere in space and then hope for the best. It's engineering-wise, it's not feasible. But there's something that actually closely follows the same concept. It also uses the stretching and squeezing of space, and that is called a laser interferometer. So now I have to, before I start the little, I'll do it because I want to pause at some point. Yeah. So so what you're going to see is a laser beam coming out of here, and it's going to hit what is called a beam splitter. A beam splitter is nothing but a semi-transparent mirror. So what's going to happen is this. Let me do that. Here comes the laser beam. It gets split by the beam splitter here. So now we have a laser beam going this, half of the laser light goes this way, the other half that way, typically in tubes that are not drawn, but they're a few kilometers long. And at the end of these tubes, there are mirrors. So those mirrors, of course, are going to bounce back the laser light. If I can now find the start, oops, if I can now find the start button again. Yeah, here it is. So the laser light, it comes back. Now, when the laser light comes back, you can set things up in the following way. So the laser light is composed of little waves that will be shown in a minute. So the laser light is composed of little waves. And you can, if there's nothing special going on, if there's no gravitational wave coming by, you can set things up in such a way, and I can even use the whatever it's called here. So you can set things up in such a way that what comes out this way will look like this. So if I look at the little waves of the laser light coming from one arm will be a wave like this. And the laser light, maybe a different color, coming from the other arm, but is going to look like this. So now we've set things up in such a way that the peaks of the laser light coming back from the one arm coincide with the dips in the laser light coming from the other arm, and the two laser beams are going to cancel each other. So no light, if there's no gravitational wave, no light is going to be seen coming out of here. So let's see the continuation of this thing here. So here we are. But now, suppose there is a gravitational wave, then of course the length, there's going to be a length difference between those two arms. Because remember that what gravitational waves do, they change distances between things. They stretch and squeeze space in perpendicular directions, and that's precisely what is being exploited here. So normally, the light beams coming back, they cancel each other. It's called destructive interference, and you don't see anything at this detector. But now if a gravitational wave comes by, then one arm is longer than the other, so the light travel time in one arm is longer than in the other arm. And what's going to happen is that the two waves, so the peaks of the laser wave coming from one arm doesn't arrive at the same time anymore as the dips of the laser wave coming from the other arm. And so now you no longer have destructive interference, and now flashes of light will be seen coming out of the detector. So that is the principle. The reality, or how these instruments really look, is very, very much more complicated, because to have any chance of seeing a gravitational waves are extremely weak, you have to have the ability to measure distances or differences in arm length that are 10,000 times smaller than the size of a single proton. That is how accurate these instruments need to be, otherwise you won't see gravitational waves. So again, this is the cartoon picture. It explains the basic principle, but there's a lot more behind it, which we won't get to today, but nevertheless. Okay, I can use this again. Now, large interferometers of this kind have been built. So there's two interferometers, top left, top right, that have been built in the United States. They are called LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. They are 4 by 4 kilometer interferometers. So these two arms with the mirrors at the end are each 4 kilometers long. Here, bottom center, you have Virgo. Virgo is also an interferometer, 3 by 3 kilometers this time, situated in Tuscany in Italy. This is an interferometer that Dutch scientists have made major contributions to. Now, those three interferometers, the two LIGOs and Virgo, they have already made detections. Okay, they have, in fact, they've routinely seen gravitational waves, but we'll get to that. Also, well, not under construction anymore, about to become operational, I would say, is another interferometer called Kagra in Japan, which is also 3 by 3 kilometers. But here, I cannot show you an aerial photograph. The interferometer exists, it has been built, but you can't show an aerial photograph because it's inside a mountain. So this is just an artist's impression, of course. And why inside a mountain? Because of you know, if you're inside a mountain, you have less seismic vibrations that might interfere with your measurement. And so that is why they did that. What else? There is also a much smaller interferometer in Germany of 600 meters by 600 meters called Geo 600. Now, this interferometer will probably never detect gravitational waves because its arms are too short, its sensitivity is not enough. But that's not the point of this interferometer. What this interferometer really is is a kind of lab to develop new interferometry techniques. Again, you know, what I showed earlier, what is an interferometer? That was only a cartoon picture. Reality is much more complicated. So all sorts of interferometry techniques were developed there and tested, and then that technology was transferred to the big interferometers like the two LIGOs and Virgos that did, meanwhile, make detections. And then finally, there's also plans by 2025, there will start the construction behind the surface of the Earth here. In India, there will be the construction of a 4x4 kilometer interferometer as well. Now, an important point here is that all these interferometers, and with these interferometers come a community of scientists, of course. We are not in competition with each other. We don't compete with each other to see the best gravitational wave or something like that. No, that would be scientifically unproductive, actually, because if you work together and jointly analyze the data, there's a number of scientific benefits. One obvious scientific benefit is, well, these gravitational waves are very weak. So, you know, if you, on the other hand, see the same shape of signal in multiple interferometers spaced widely over the surface of the Earth, then you have more confidence that you're actually seeing a gravitational wave. But there's another reason why we should work and do work together, and that's the following. So there are sources of gravitational waves, we'll get to that, but for instance, when two neutron stars collide with each other, they emit not only gravitational waves, but also light, ordinary light. Now, what you want to have is the ability to tell your fellow, the astronomers, the ability to tell them, look, we are seeing gravitational waves, they seem to be coming from a certain part of the sky. If you guys point your telescopes there, maybe there's something for you to see as well, and then we will have more science to look at. And the way it works is, how do we localize things on the sky with gravitational wave detectors, with a network of gravitational wave detectors? Well, my gravitational wave comes, it hits the first detector in the network, then some milliseconds later, it hits the second one. Sometime later again, it's the third one in the network. And from those different times of arrival, you can actually infer where in the sky something happened. So what are the things in the universe that emit gravitational waves that we can hope to measure? Well, these are the four main ones. There may be more. We are hoping to find the unexpected, of course. But one thing we are hunting for is the merger of two black holes or two neutron stars. Those are actually the kind of gravitational waves we are seeing now. They come from that kind of source. And so what happens is you have two black holes, let's say they're in orbit around each other. They spiral towards each other because gravitational waves, they carry energy. So energy is lost from the system because of gravitational waves carrying away energy. So the orbital energy decreases. The two objects come closer and closer and closer together until they merge to form a single black hole, which then vibrates a little afterward until it quiets down. This we will get back to. This will be the main focus of this talk because, again, those are the signals, the types of signals we are seeing now, and that is where all the hot science is now, right? The future is something that we'll get to. But to quickly describe other sources that we also want to see, suppose you just have one neutron star without a companion. So there's not two objects in orbit around each other, just one neutron star. Well, if that neutron star is fast spinning and a little bit asymmetric, a neutron star can have a little mountain on it, then that too can be a source of detectable gravitational waves. And by the way, neutron stars being so compact and the gravity on their surface is so strong that the maximum height of a mountain you can have on a neutron star is 1/10 of a millimeter. Okay, the Himalayas on a neutron star are 1/10 of a millimeter. Also, not to get too gruesome, but if you as a person, you were to stand on the surface of a neutron star, your body would not be able to withstand the gravity, and very soon you would be an extremely thin puddle of a height of no more than 1/10 of a millimeter, spread out over probably a couple of football fields, right? Now, another source of gravitational waves are supernovae. So supernovae, again, asymmetry is the key. So if there has to be some amount of asymmetry in the system, in the explosion in this case, and then we might see gravitational waves from those two. And then what will probably end up being the holy grail of the field is gravitational waves, so-called primordial gravitational waves that originated from a fraction of a second after the Big Bang. And these are relic gravitational waves that are probably still around us, probably zooming through this room, coming from all directions at the same time. And if we were to see that and understand what they are, we would have access to what happened a split second after the Big Bang, when energies were at play that are millions of times stronger than anything we can generate on Earth, like anything we can generate in the Large Hadron Collider at CERN. But again, here we're going to focus on the top left here, the merging black holes and neutron stars, because those are the things we are seeing now. So I already kind of explained how it happens, right? So you have, suppose it's two black holes, then they spiral towards each other as they lose orbital energy because of emission of gravitational waves. Then comes a moment of last stable orbit, as it's called, and then the two objects plunge towards each other to form a single black hole, which will be highly excited, will be vibrating like crazy for typically a few milliseconds, and then it dies down and it becomes a stationary black hole. Below, you see sort of the shape or the amplitude as a function of time of the gravitational wave that comes out. So first, during the in-spiral, you see the amplitude, the strength of the wave steadily increasing. You also see the frequency increasing because the tops of the waves here are getting packed closer together. Then this one spike here is the merger itself, the formation of the one black hole. And then it sort of trails off in what we call a ring down. So that is the newly formed black hole that rings like a bell until, it has expended its energy. It becomes a quiet black hole. We have made many detections already of that sort. So we have now made in the order of 100 detections. This is a very busy plot. Let me explain how to read this plot, actually. So first of all, you see these markers. You see typically two blobs connected by an arrow pointing to a third blob. Well, each of those are a detection of two black holes or two neutron stars merging together. And they are arranged from left to right in terms of date of discovery. Okay, so this was the first one. This one was the first one, was discovered, so 15/9/14, so 14th of September of 2015. And then come the other ones. This third one, 15/12/26 was on the second day of Christmas of 2015, and so on and so on. But anyway, so you see a lot of sets of two blue blobs being connected and going to a third blob. Now, on the left-hand side, on a vertical axis here, you can read off what were the masses. We can measure based on the shape of the signal, what were the masses of these black holes. So two black holes with different masses that you read off on the left, 1 solar mass to 5, 10 solar masses, up to 200 solar masses, they merge and they form a black hole, well, with a higher mass, as one would expect. So now that is not all we see. Another thing we see is neutron stars merging. So the neutron stars are marked in orange here. And so two neutron stars in spiral, they merge together to form, we don't know, actually, probably a black hole, but we're not yet sure. And actually, that is one thing we need Einstein Telescope for, but we will get to that. So we've seen in spirals, at least, of neutron stars. And then you can also have a neutron star, orange again, merging with a black hole, blue, to form a slightly more massive black hole, neutron star black hole mergers. Okay, so that is the census so far. You see that the overwhelming majority of the mergers that we see are from black holes, and there's a reason for that. The reason is that when you have black holes have typically higher masses than neutron stars. So when things with a higher mass merge together, then the strength of the gravitational waves is way more. Therefore, those are events we can see to much higher distance. Therefore, we're going to see more of them, right? Makes sense. All right, but nevertheless, among that multitude of detections, there are a couple of special events. So one special event was GW 190412. First of all, the naming. GW for gravitational wave. And then the naming convention is the date of discovery in terms of year, month, day. So this one was discovered in the year 2019, 4th month, 12th day. Okay, that's in any case, what was it? Well, it was a binary black hole, two black holes merging. But the special thing about this one was that the two black holes had very different masses from each other, 8 and 30 solar masses. And when that happens, you don't just get gravitational waves, you get gravitational waves with overtones. Okay? So that is sort of what is illustrated here. First observation of overtones in a gravitational wave. Then there was GW 1908-14, similar naming, 2019, August 14th day. This was a black hole of 23 solar masses merging with an object of 2.6 solar masses. What was the significance of that? Well, 2.6 solar masses, we don't know yet for sure, but it's probably too massive to be a neutron star, because then if you make a neutron star too massive, it collapses into a black hole eventually, right? So it's probably was too massive to be a neutron star, but it's also hard to see astrophysically how to form a black hole that light. So what was this thing? Well, we don't know, and we need to see way more of these events and study them and see what is going on here. Then 1905-21 was two black holes again, but with huge, for our standards, huge masses, 66 plus 85 solar masses. Now, the special thing here is black holes that massive cannot be formed out of the collapse of an ordinary star. So normally what happens is you have a big, big star, and at the end of its life, it collapses and it forms a black hole. Well, you cannot make black holes this big using the collapse of ordinary stars. So the suspicion is that both of these objects actually were the result of the previous merger of two black holes, each of them. And then the resulting black holes found each other somehow, became a binary, and that one formed a more massive black hole. In fact, the resulting black hole, pardon me, had 142 solar masses. Now, everybody here can do math. If you add 66 and 85, you don't get to 142. There's 9 solar masses missing. Well, where did the 9 solar masses go? They were emitted as gravitational radiation. 9 solar masses worth of energy, E equals mc squared, right? 9 solar masses worth of energy emitted away in gravitational waves. And then we have the neutron star black hole examples. Here are 2 examples. By the way, my list of special events ends in early 2000. You might wonder why. Well, the reason is that in early 2000, the detectors were shut down for a major upgrade so that they would be more sensitive. But then came COVID, so that slowed down the upgrade. And then the upgrade eventually got finished. And since May of this year, the detectors are operational again, and they're taking data. So they're discovering new things, except we're not allowed to tell you yet what they are, because first we want to analyze them privately, and then we'll put out papers and publish in journals and whatever, talk to the press. But more is to come. What are gravitational waves good for? Well, one thing they are good for is they give us access to really strongly curved and very dynamical spacetime. Strongly curved means, well, you have strong curvature of spacetime. Dynamical means that the curvature of spacetime is changing very rapidly. Now, how to read this plot? Well, on the horizontal axis, there is a characteristic timescale associated with some astrophysical event or object or whatever. And on the vertical axis, there is the strength of spacetime curvature. We in the solar system, we live here. Very long timescales. It takes rather long for the Earth to go around the sun, and also very weak spacetime curvatures. So if you want to test Einstein's theory of general relativity, this is the wrong corner of the plot to be in. You can do some tests, like there's the famous perihelion precession of Mercury, which is, I'm not going to go into details, but it's something that cannot be explained by Newton's theory, but it is explained very accurately by Einstein's theory. Nevertheless, this is the most boring part of this plot. Until recently, the most general relativistic object that had been seen through radio observations, not gravitational waves, was called a binary pulsar, so 2 neutron stars going around each other, but still very far from merging. So these are 2 neutron stars that will only merge 30 million years from now. But you can tell already that their orbits are shrinking just using radio telescopes, radio observations. But even that one comes with fairly long timescales still, and also its spacetime curvature is nothing to write home about particularly. Our gravitational wave detectors are way up here. Extremely strong spacetime curvature, and also spacetime is changing over timescales of less than a second. If you really want to test general relativity, this is where you need to be, okay? And this is where we are. Okay, So now that is one thing. So what is the dynamics of space-time? Is it really as predicted by general relativity? We're testing it. Another thing you can do is look at the propagation of gravitational waves. So gravitational waves have a long way to go from their source to us, typically a few billion light years. Now, if you take a gravitational wave, and this is a little bit technical maybe, but if you take a wave of any kind, if you separate it into its different frequency component, its Fourier components as it's called, then in the case of gravitational waves propagating in vacuum, all those components, they travel at the same speed, namely the speed of light. That is the prediction of general relativity. But suppose it were not so. Suppose that general relativity is wrong in this. Well, what would happen then is that some frequency components travel at a different speed from others. And the way you would notice this is a wave would get either compressed or stretched, okay, the wave as a whole. And so this is how you would be able to tell. But this effect is something that is cumulative over the enormous distances that gravitational waves have to travel to reach us. And so therefore, we are very, very, very sensitive to this kind of effect. We can really dig deep into the data and see what happens. Now, if there is dispersion of gravitational waves, again, forbidden by Einstein, but Einstein may be wrong. If there is dispersion of gravitational waves, what could be the cause of it? Well, you may have heard of the graviton, which is the hypothetical particle that mediates the gravitational force, is sort of the messenger particle of the gravitational force. And it is expected to have zero mass. But if it has non-zero mass, then gravitational waves would undergo dispersion, as in the little animation that I just showed. And again, this effect is cumulative over these large distances. So you can actually use the fact that we don't see dispersion, you can actually use that to put an upper bound on the mass of the graviton. And the best upper bound we have obtained so far is that if the graviton mass is non-zero, it has to be smaller than about 10 to the minus 23 electron volts. That is much, much smaller a mass than any particle we have ever heard of. Okay. Also, the photon, the particle that mediates the electromagnetic force, is another particle that is supposed to not have rest mass. Also about with different methods, bounds have been placed on the mass of the photon. Well, we do better than the photon upper bound by 5 orders of magnitude, which we are very proud of. So then you can do other things like once you have seen enough binary black hole mergers and you've measured their masses and so on, then you could sort of try to start inferring what is the mass distribution of black holes in binaries. And the reason that's interesting is that it tells you a lot about how binary black holes form, how they come into existence in the first place. And we're starting to do that. So you know, you have these curves. It's a busy plot, right? So you have multiple curves. You have these blue bands are uncertainty bands. There's uncertainty on the measurement still. And that's because we've only seen 100 binary black holes. That's it, right? So we want to go further. What is the structure of neutron stars? So as I mentioned, we don't just see binary black holes, we also see mergers of neutron stars. And that is below, you see a computer simulation. So two neutron stars spiral towards each other. They merge to form a rather complicated bar-shaped object here. And then, yeah, whatever else happens after, we're not sure. By the way, the in-spiral signal is what you can see here in data from LIGO Hanford and Livingston. So these streaks here, this is frequency as a function of time. This streak is the in-spiral signal in both cases. It is also present in the Virgo detector, except you can't see it by eye in this plot. You need specialized techniques, but it is there. But anyway, with existing detectors, we only see the in-spiral because the merger, actually the most interesting part, right? The merger happens at frequencies that are too high for our current detectors. For that, we need an Einstein telescope. And actually, binary neutron stars are super interesting in a variety of ways. So in 2017, we actually saw a binary neutron star in spiral, not the merger itself, but the in spiral we saw with gravitational waves. Then that thing emitted a burst of electromagnetic radiation of very high energy called the gamma ray burst. And the gamma ray burst arrived at about the same time as the gravitational wave, from which we were able to infer that the speed of gravity is the same as the speed of light to 1 part in 10 to the 15, okay? Because the gamma photons are just light, and we're also seeing the gravitational wave. This is a prediction of general relativity that the speed of gravity is equal to the speed of light. We're able to test that to enormous accuracy, and a number of alternative theories of gravity to do with cosmology and so on went immediately in the waste paper basket because of this one joint observation. Now, thanks to the fact, also with the network of detectors I mentioned, you can localize stuff on the sky. You can sort of tell where in the sky that the gravitational wave came from. Well, astronomers did look in that patch on the sky, and they found an afterglow, the afterglow of the collision here. This is a galaxy, but nearby it, there is this thing that wasn't there before. And if you look at the spectrum, so basically how much of each wavelength of light is present in what you see here, you can infer that lots of heavy elements are present there, like gold, platinum, uranium, and so on, which is as you would expect from the merger of two neutron stars, because you may know that in an atomic nucleus, you have protons and neutrons, but the protons they all have this like charge, so they repel each other. The protons repel each other. It is the neutrons that keep the atomic nucleus together. But a heavy atomic nucleus, one that has more protons, needs proportionally more neutrons to keep it together. And so what is the best environment to make things, atomic nuclei that have lots of neutrons? Well, probably the collision of two neutron stars, right? So we now believe, also thanks to this discovery, that almost all of the gold in the universe, so the gold in this ring, for instance, came longer time ago from the collision of two neutron stars, also platinum and uranium. The gold was smeared out broadly in the press. So the gold that got created with the collision of two neutron stars. At the time, I had a chat with a colleague, and I was mentioning this. The press is fixated on this gold, and she says, "Well, yeah, but, either you tell the journalists that a lot of gold was created, but it's too far to get to, or you tell them that the aliens now have a lot of uranium. Your choice." Now, it is also binary neutron stars together with electromagnetism. They are a new way of measuring distances in the universe and map out the universe as a whole. This I won't go into so much. And then, the interiors of neutron stars, what do they look like inside? That is maybe actually the biggest problem in stellar astrophysics today. We don't know, is the real answer. So now I've already sort of hinted at limitations of existing detectors, right? So one limitation is that, if I can go back, one limitation is that if you look at two neutron stars, with current detectors, we only see the in-spiral signal because the merger, which is actually the most interesting, is too high frequency for us. That's one reason why you would want new detectors. There's other reasons as well. Well, new detectors and actually new types of detectors are being devised. In June of this year, you may have read in the newspapers about a new way of detecting gravitational waves that has nothing to do with interferometers. It works in a totally different way. Namely, you look at neutron stars in our Milky Way that are at a large distance from each other. And neutron stars, you may know, are pulsars. So they emit pulses of electromagnetic radiation. You see blips coming from certain location on the sky, again with radio telescopes, not with gravitational wave detectors. But anyway, these neutron stars, they're very stable clocks. They're the best clocks that the universe produces. And so normally these blips come in exactly the same time intervals, always. Now, one thing that a gravitational wave does is to stretch and squeeze space. That is what interferometers exploit to detect gravitational waves. But what they also do, gravitational waves also mess with the local flow of time. And so now the pulses will arrive at different times. And if you can correlate with neutron stars that are so far apart in our Milky Way galaxy that they can be influencing each other, if you can see a correlated effect in many of those neutron stars, you can infer, we have a gravitational wave coming by. And this is a way of measuring gravitational waves with very long wavelengths, because your detector is now the size of a Milky Way, right? So now you have Milky Way-sized gravitational wavelengths that you're sensitive to. Anyway, so that was in the news June of this year. Then in the future will be the Laser Interferometer Space Antenna, or LISA. That is a space-based detector. It will consist of 3 probes in orbit around the sun. Those probes will exchange laser beams so that you have a kind of interferometer again. And The distance between the three probes will be in the order of 1 million kilometers. You can do that, put them so far apart because you're in space. There's literally space for it. So yeah, and so you have these million-kilometer long interferometer arms, and now you're going to be again sensitive to wavelengths that are way longer than what you would be sensitive to on Earth. Not as long as with this method, but still you would be seeing mergers of what are called supermassive black holes, not black holes with tens of solar masses, but millions to billions of solar masses, because those are the objects that produce things with a long wavelength. So that's LISA in space. And Einstein Telescope, that is the project that we are concerned with here. So Einstein Telescope is to be built probably around 2035. It'll be an underground facility, a triangle of 10 by 10 by 10 kilometers. Inside the triangle will be 3 detectors, not L-shaped interferometers, but V-shapes. And you put 3 of them, you arrange them in an equilateral triangle. So underground, again, to suppress seismic vibrations. Also, just the various components of Einstein Telescope will be seismically isolated, as it is called, in a much better way. So noise suppression will not just be because it's underground, but because of high tech, and also more sensitive optics, etc., etc. And this will give you a factor of 10 improvement in sensitivity over LIGO and Virgo, even if LIGO and Virgo were already at design sensitivity, which they're not. Now, what is the significance of a factor of 10? If you're more sensitive by a factor of 10, you can see a factor of 10 further into the universe, which means that you're covering nearly the entire visible universe. So that means you're going to see a lot of sources, right? A lot of gravitational wave detections, probably in the order of 100,000 per year from merging neutron stars and black holes. But also the closer by ones will be extremely loud in your detector. They will really show up in your detector, right? So this will allow for precision tests of general relativity that have never been seen before, that kind of accuracy. You will be mapping out the population of black holes. I was talking about what is the distribution of masses of black holes, because that tells us about how binary black holes come into being. And we will have access to the interiors of neutron stars, because we will be able to look at high frequencies and actually see the merger itself of 2 neutron stars, but with gravitational waves. That, by the way, is something that LISA cannot do. LISA will not see merging neutron stars. And so that also means, by the way, that Einstein Telescope and LISA are complementary to each other. They don't do the same science. They look at different things. What Einstein Telescope will really do for us is probe what is called the dark ages of the universe. So what do I mean by that? First of all, what does this plot show? Well, the plot is to be read from left to right, with increasing time starting from the Big Bang, or going from right to left, you're going back in time, right? So if the Big Bang is here, we are at 13.8 billion years after the Big Bang. Well, here's the Big Bang then. The first stars got formed around here, so a few 100 million years after the Big Bang, and then in turn galaxies got formed, and so on and so on, and then you get eventually the universe that we see at the present day. Now, black hole mergers with current instruments, LIGO and Virgo, can only be seen up to about here. So looking back in time to about 8 billion years after the Big Bang. That sounds impressive maybe, but it isn't, because we only see our cosmic backyard that way. Then recently launched was the James Webb Space Telescope, which is not a gravitational wave detector. It is in fact an infrared telescope. It looks in infrared electromagnetic radiation, but it can also tell you a little bit about black holes. For instance, you can have very massive black holes that accrete a lot of matter. A lot of matter tries to cram into that black hole. Just before it falls in, it will be compressed so much that the temperatures will be so high, you get intense radiation. It glows like an ember, that matter just before it falls into the black hole, and then it becomes invisible, of course. But James Webb Telescope can see the signatures of that. But here's Einstein Telescope. Einstein Telescope can see all the way back to a time that there weren't any stars yet. Now you might ask, why would you build a machine that can't see anything? Because there wasn't anything to see, because there were no stars to collapse to form black holes, right? Well, that's the point, the unknown. But of course, you have to motivate that. So what are the unknowns? What American politician Cheney, I guess, there's known unknowns and unknown unknowns and so on and so on. Well, known unknowns are there primordial black holes? What do I mean by a primordial black hole? Well, a primordial black hole actually isn't formed from a star, it's formed here, shortly after the Big Bang, when there were huge density fluctuations. That, you know, in one place there could be way more matter than in some other place, and in a place with a lot of matter, it can collapse and form a black hole. And now you have a leftover black hole from the era right after, split second after the Big Bang. We might be able to see those. Another example is, more speculative maybe, is cosmic strings. So what may also have come out of the Big Bang is one-dimensional structures, so not point particles like electrons, but one-dimensional structures, very infinitely thin. And when they cross each other, they emit a burst of gravitational waves. So if we start seeing bursts of gravitational waves coming from that far back, probably we're seeing cosmic, or maybe we're seeing cosmic strings, and that's what we're so those are the sorts of things we want to explore in the dark age, but most likely big surprises await us there. Okay, so now with big expectations come big responsibilities, and also the need to develop much better technology, right, than is now in interferometers like LIGO Virgo. But that to develop that technology, it can't just come out of nothing, right? You have to build things, you have to test things. And there's a test facility not far from here at Maastricht University called Einstein Telescope Pathfinder. Now, Einstein Telescope Pathfinder is not a gravitational wave detector. It's not meant to be. It's a lab where all sorts of techniques are being tested. An example, what will be tested is cryogenic mirrors. So cryogenic means very cold. If you have very cold mirrors, you're more sensitive to gravitational waves. But now comes a conundrum. If you want very cold mirrors, think of your refrigerator. A refrigerator, yeah, it makes things cold, but it vibrates. When it switches on, it vibrates, right? But if you want a very cold mirror, but at the same time, you don't want vibrations, you have a big technical problem right there, right? So how do you solve that? Well, that is a question for Einstein Telescope Pathfinder. Also, new mirror coatings. If I look at the mirror in the morning, the mirror will reflect fine, but it won't reflect perfectly, right? Some light will be absorbed by the mirror rather than just being reflected. But that's not good. We want mirrors that are as reflective as possible. And how do you, well, what would that be then? What kind of materials do you need? And also mirror suspension systems. These mirrors are suspended from thin wires, again, to prevent all sorts of vibrations and so on. Einstein Telescope Pathfinder is getting very concrete. This is a photograph from about 2 weeks ago. So it's getting there. It's under construction, and next year it will be a fully functioning lab, and all these things here can be tested and developed. But we here, and now I come to, well, this is the introduction to the rest of the afternoon, actually. So Einstein Telescope data analysis will also be a lot more difficult than what it is in the case of LIGO and Virgo. So one reason is that signals will be visible in the detector for much longer times. Like, for instance, I mentioned that binary neutron star in spiral. LIGO and Virgo saw it for just over a minute. It was visible in the detector for just over a minute. In the case of Einstein Telescope, this will be hours or up to days. Now, our current data analysis techniques, they have no way of coping with this. This is already the first out of many problems, by the way, the first problem. So if we were to be presented with data from Einstein Telescope tomorrow, suppose that tomorrow already miraculously Einstein Telescope is underground, it's ready, it's taking data, we would be able to do nothing essentially with that data. We'd be screwed because our current techniques, they will not work, not with the size of the computers we have, and also not if you were to scale up compute power. You know, Moore's law is already failing. So you're not going to get there. You need to do something more smart. Rather than build a bigger computer, because the bigger computer won't work. But another thing is, I mentioned that Einstein Telescope could see in the order of 100,000 signals per year. Now, of course, then those signals in the detector output are going to start overlapping with each other, right? And now how to pick them apart and study them and do this precision science that is being promised. How are you going to do that? So that's an extremely hard data analysis problem. And then there's a number of other problems, actually, more technical. But then something that will be prominently present in the talks after are instrumental glitches. So I mentioned that in Einstein Telescope, you have signals that will be visible in the detector for an extremely long time, like days. But there are also signals, not from neutron stars, but from very massive binary black holes, like 10,000 solar masses, that will be in the detector for only a tiny fraction of a second. So then frequency as a function of time again, rather than the streak I showed earlier, you get, well, actually I have to point here, you get something like this, okay, a blip. But that looks uncannily, or more or less, to what is shown on the left-hand side, which is not a gravitational wave signal. This is a temporary malfunction in the instrument, like a mirror shaking for some stupid reason that has nothing to do with gravitational wave. So a temporary misbehavior, in a sense, of the instrument. And how do we tell those together, or apart rather? So that is a big challenge. And so in all of these things, well, what is very much in the news nowadays, but for a reason, is artificial intelligence, because I think many of us believe that artificial intelligence and machine learning are going to be the key towards solving these problems. So here's a summary. So I hope I've convinced you that gravitational waves are a new and kind of unique way of seeing into the universe, test the dynamics of space-time in a way that could not be done in any other way. Map out the population of black holes, look inside neutron stars, understanding the universe at very large scales. What Einstein Telescope will do for us is to turn first of all, turn gravitational wave science into a precision science. A colleague in the US who is working on a similar idea as Einstein Telescope once put it as follows. It will sound crude, but he said, well, LIGO and Virgo are the worst possible imaginable gravitational wave detectors because they are only just barely capable of seeing gravitational waves. True, but if you're only just capable of seeing gravitational waves, you're not going to be doing precision science, right? And so that is why we need to take the next step and go to Einstein Telescope. And then, as I mentioned, Einstein Telescope has then the benefit of looking all the way back into the dark ages of the universe before any stars have been formed, and a lot of surprises await us there, I would guess. But with that come challenges. So first of all, hardware, the instrumentation itself is extremely difficult, and there's a tight deadline. All of this needs to be developed before 2035. But equally important, new data analysis challenges are present, and they also need to be addressed before that date so that we can actually have our precision science and look back to the dark ages of the universe. And I'll stop here.
Some questions, or you have probably posed some questions, or we move on, look at the timing, and we do the talk because we have enough time for drink and the bites. Yeah. Okay, great. Thanks. Thanks, Chris.
Here's
So it's a very nice inspiring introduction, and that's a little bit gave you the idea how time could travel. So actually we're using the telescope to travel back to billions of years ago. And now, yeah, welcome Melissa, who's representing Stefano and giving a little bit more scientific insights on how we read those data by using the AI. Welcome.
Okay, thanks. Hi. Well, I'm actually Stefano with a wig. No, I'm just kidding. Like, the poor guy has a fever, so he couldn't make it today, but that's why I'm here. My name is Melissa. I'm a PhD student at Utrecht University, and I actually did my master's in data science, but my bachelor was in physics. So I have kind of a mixed background. And today we're going to talk about feature anomaly detection for gravitational waves. So Chris talked quite a lot on how detectors work, and actually the data of a real gravitational wave, a detector looks something like this. So it's essentially a time series. You can think about, for instance, like a seismometer that records earthquakes and stuff like that. So this is kind of similar, but this is much more sensitive because, as Chris said, it's like 1/10 to the power of 4 the size of an atom or something of a proton or something along those lines, right? So here we have quite a lot of mix of information. We have, as I said before, seismic noise. We have also quantum noise. So this is very dependent on how well we are able to isolate the mirrors that we have in the detectors, but also on how well we position them, because we have lasers coming and going back and forth. So the whole point or main idea behind this work that we are doing in the Einstein Telescope Technologies, it's essentially to find anomalies. So we want to understand what's buried within this noise. It could be, for instance, a gravitational wave, but also it could be a technical problem like an artifact occurring in the gravitational wave data. Like these detectors are really, really complex, and they have a lot of parts together. So once you put everything together, you have your detector. There's some problems that might arise, and those are what we commonly call glitches, which are essentially artifacts that come from different parts in the detector. So here in this time series, this all looks quite noisy, and in particular, we have this part that looks a bit different. So the idea behind this work is to understand where this difference is coming from. That's why we're actually working with anomaly detection. But first, let's start with what searches of gravitational waves look like. So we can talk about, we'll talk about the searches of what the things that we know. So Chris spent quite a lot of time explaining about binary black holes and binary neutron stars. Those are the things that we actually know because they're well modeled with general relativity. So also we have other type of searches, which are essentially the searches for the unexpected, the things that we don't know. And that's where completely data-driven algorithms come into play. And that will be an example to look for those will be, for instance, supernovae, because explosion is so complex. It's a fight between pressure and gravitation that essentially makes this quite burst-like. So this doesn't really have a shape that we know. It can vary depending on the components of the explosion, and essentially that's why we want something having minimal assumptions. And also in the future with Einstein Telescope, we'll have the problem that Chris mentioned about overlapping signals. We know what black hole signals and binary neutron star signals are, but when they start overlapping, they will make this crazy shape. So we don't really know how to analyze. And that's one of the key problems on why we also want to do searches for the unknown, right? So what is anomaly detection and what is the search of the unknown? So anomaly detection in a nutshell is when we have, let's say, a high dimensional data, like for instance, here in this space, we have all these blue dots, and we want to understand the general trend of the data. So everything looks kind of like clustered together, but here we have this anomaly here that deviates quite a lot from the general distribution. So statistically, we can say that this is an anomaly because it's quite far apart from the rest of the population. So essentially, that's what we want to do here. The only thing is that we want to do it with time series. And time series are complicated. They are not images. We humans are prepared to learn about images because we actually walk every day in three-dimensional space. That's why we are more ready for images than time series. And as I said before, gravitational waves can get anomalies coming from gravitational wave detector data can get anomalies from gravitational waves themselves, but also they can have glitches. So for instance, in the third observing run, so now we're in the fourth observing run, so the previous run, we were detecting one gravitational wave every 2 weeks. So essentially we have 2 weeks of normal data where not really a lot of things are happening. Mainly we have artifacts from the detector and then suddenly a gravitational wave comes in. So we want to tell apart this gravitational waves from the rest of the data, and that's why we can actually learn a lot from the normal data, something that won't really happen with Einstein Telescope, unfortunately. And then what we want to know is what are the main characteristics of the data, the main features. And for this, what we are doing is essentially taking a time window, and this time window will be slided over the whole time series. And at every step in this time window sliding, we'll calculate different features that I will tell you in a more like deep level what they are. So they will represent in different frequencies what we are looking at. And from those features, we are gonna see what are the main differences or the main trend of the data to locate those anomalies. So these are some of the features that I was talking about. First, every time window, we can look and how the variance at low frequencies, we can also look at the variance at high frequencies. We can also calculate the maximum value in this time window. And also we can have other measures, like for instance, how complex this time windows is. If it's more like Gaussian noise, like it doesn't really have a structure, or if it actually has something in there that's kind of structured, like for instance, like a glitch or like a gravitational wave. And something else that we can calculate statistically is the KL divergence, which in a sense, it's essentially seeing how similar this is to normal data, to data without the structure. So we can combine all the sort of features that it's not limited to this one. So it's something like very flexible. And then we can essentially combine it all together and here you have all the different plots of all these measures. And what you can see is that they are actually clustered together, as we saw at the very beginning with our mock data. You can see some red dots over here that actually deviate quite a lot from the general trend of the distribution. So essentially what we want to look at, it's what are these anomalies within the detector data. So if we go back into the detector data, once we have selected these specific anomalies, we can see again the frequency time plots where we actually have nothing really going on. So this will be the excessive power, the z-axis. And here you can see something like an artifact, a glitch that's actually in the data that we were able to find because of this algorithm. And then we can kind of analyze what is the population of these glitches to solve something within the detector, right? And this is a bit more technical. So this will be a very general description of how the pipeline works. So the first thing is that we want to whiten the data. So what is whitening? So here you have a plot which is the frequency and the parallel spectral density that you can understand as the contribution of each frequency. So you can see that there's so this frequency is essentially from noise from the earth, right? Like seismic noise, quantum noise, cars, thunder. So you can see that it's pretty high on the sides, but it's kind of low in the middle. So those are the frequencies that we're interested most for instance, by black holes, by neutron stars. And we want to push this down. That's how we are essentially advancing the science of the detector. And Einstein Telescope, you can see that it won't have a lot of noise compared to the other detectors. And this is the sign, right? Then you have other unexpected things, and that's why this looks so messy. You have, for instance, noise that comes from the electricity power. And this is the current thing that we have, but we want to highlight in the middle where the gravitational waves are, this region of gravitational waves. And there, what we do is essentially flatten all these frequencies. When we flatten all these frequencies, we can highlight the gravitational wave that's in this band, for instance. So that will be the first step. Then we compute all these different features that we talked about before. It's not only restricted to the ones that I showed, but then we can aggregate them and fit them into a multidimensional probabilistic model. This can be like a very big wording, but it's essentially a model that takes all the data and gives you a probability or an anomaly score if this data is normal or not. And that's the main idea. And then afterwards, we kind of need to compute the likelihood that this is an anomaly or not. And then we rank the anomaly. And with this, we are able to detect artifacts and gravitational waves. So the recap of everything that we talk is that this work is called feature anomaly detection for gravitational waves, because we are assessing different type of features to detect them in an anomaly detection fashion. We're looking at the unexpected. And also this will be only for gravitational wave data, but it's not limited to this. This could also be applied in any other company that's dealing with time series. So this is a very flexible framework for any kind of application. Oh, sorry. And then what's next? Well, the thing is, we are still looking at and assessing what are the best features for this work, and also how to compute this anomaly score, this likelihood in a way that makes sense. So the final idea is to set this as a pipeline for production in the LIGO-Virgo collaboration. And that's everything from my side. Thanks so much for listening.
Thank you a lot. As Melissa explained, this is called anomaly anomaly detection. Actually, we use it in a lot of other areas like some security systems, also detecting when there's a fraud, and also in a lot of other areas. So this is a kind of generalized AI techniques being used in different things. And that's where we also try to use it, because most of the data, as they said, it's a noise. Even the cars are running on the streets, that's generating those signals that are captured by those telescopes. So we want to know what are the noise, the background, those white noise, and which are the useful things we can use. So that's a great example, actually leveraging techniques which are also be able to apply to a lot of other areas. So that's the purpose of the project, to inspire other companies as well. And welcome the last talk before we finalize our day. Tom, it's your stage.
Thank you. Good afternoon. My name is Tom Dooney, and I'm a PhD student at Open University. Like Melissa, I also studied my bachelor's in theoretical physics and then studied my master's in data science close by in Maastricht. So we have similar backgrounds, and then again, we found ourselves working on similar research. Today I'm going to be giving a presentation on using conditional GANs for generating gravitational waves data. We'll have a little discussion on what GANs are and what they can be used to generate. So detecting gravitational waves is difficult. We can see a GIF image that we saw earlier during Chris's talk of these colliding neutron stars, which are then picked up by some land-based interferometer here on Earth. And then these manifest in the detector stream, as we saw, by these lasers interfering with each other. And you can see this light blue waveform here is the gravitational wave deeply embedded in the background detector noise, which is shown in the dark blue. So this is the dark blue is earthquakes. This is people getting up to go to work in the morning. And then we have this really massive event that happened so far away that by the time it reached Earth, it was very, very small. And to use the analogy with sound, it's very, very quiet relative to all this stuff that's happening here on Earth. So finding them can be very, very difficult at times. Sometimes they're loud. Sometimes, a lot of the time, they're very quiet and they're difficult to isolate. So this problem becomes even more difficult when these glitches occur that we saw a little bit earlier. I'm actually showing the same image here, where we have this black hole merger on the right, and then we have a very similar looking event that seems to be happening. But this is actually just an instrumental glitch, or in this particular case, I think that they're not even too sure exactly the source of it. So these things get in the way of the physicists trying to understand important theories about the universe. So gravitational waves, GWs, and glitches, we want to identify both of them where they happen. So at the moment, for this type of presentation, eventually we want to understand this is a glitch, this is a gravitational wave, but we want to know when these things emerge in noise, in the background noise. So sometimes when they're loud, they stand out, and I show this orange waveform of, on the top we have some glitch events in their time series form, and in the bottom I have the merger of some simulated black hole events. And in this case, if you look at the blue background, these orange waveforms, these events, when they happen, they contribute quite a lot to this blue background. We can kind of see it spiking where that happens and so on. When we say something is loud, it has a high signal to noise ratio. So the signal is popping up quite clearly against this blue background. And sometimes they don't stand out very much at all, and they're very quiet. And then in that case, it can be even harder to pick them up. And here we can see that this orange waveform isn't contributing as much to this blue detector background as in the previous case when they were reasonably loud. So to try and identify where these things happen in the detector background, we use some sort of detection model. More and more nowadays, people have been resorting to machine learning, deep learning solutions to these type of things, as well as the more traditional methods. But for the beginning, we'll just consider this just an arbitrary machine learning detection model. And we train this model, and then we give it some sample and we say, hey, is there a noise in here? And then this model will say, oh, 1, yes, good. There's a signal in there. So there's something of interest that we need to try and understand. And when they're loud, these detection algorithms can work reasonably well. And then we also want them to know, we also want them to be able to tell us, oh yeah, there's actually nothing really of interest in there. This is just standard background. Don't worry about it. Oh, it'll pop out a 0. Cool, happy days. So sometimes when these signals are quiet, these detection algorithms don't work as well. And later down the line, that might cause problems. So the more quiet a signal is, intuitively, the harder it is to detect. So sometimes they will output the wrong answer for us. And now we're just going to have a little look at an application of using GANs for learning these types of underlying waveforms that can pop up in the detector background. First, we're going to take a little look at how we can train them and what we might train them on. So GANs stands for Generative Adversarial Network. And in a GAN, we've got a generator and a discriminator. And the generator is what does the generating. It's what puts the G in GAN. And we'll have a little bit of a closer look at how that works in the next slide. But for the moment, let's just consider 3 types of signals. We won't really care about what exactly they are at the moment, but we just have some signal class 1, signal class 2, and signal class 3. First 2 look kind of similar, and that's because they kind of are. They're both glitches. And the third one is the last very short time span of the last quarter of a second or so of these 2 black holes colliding. And for the moment, we just consider these number 1, number 2, number 3. So if we just want to train a GAN, we can just consider one of these classes, and let's see how it learns. It learns, okay, we're learning one shape that seems to comprise these glitch signals. And then, oh, wait, there's more different shapes here. It's not just a one shape, and the GAN slowly learns that there's some diversity in this data set. And in the GAN, how this actually happens is that the generator has the objective of generating realistic samples, while the discriminator has the objective of telling what is fake and what is real. What comes from our actual signal distribution and what comes from this generator. So they both start off and they're both bad at their jobs. And the discriminator then slowly starts to realize, wait, that doesn't look real. I've seen real, and that doesn't look like it. This slowly encourages the generator to get better at its job of generating a sample that looks realistic. And this is what we end up seeing during the training phase while we're training the GANs, that slowly it just learns this one shape. And then eventually the generator starts doing well at its job and starts generating more realistic samples from across the whole distribution of what these signals can look like. So we consider these 2 networks. They're both neural networks, which you've probably all heard about in some way, shape, or form. And they're both 2 competing networks that play in a game against each other. And they can be considered adversaries. So that's where the A in GAN comes from, generative adversarial networks. So we can do a little bit more with GANs then. We don't just have to train on this signal class 1. We can also train on more signal classes, signal class 2, signal class 3. And we can tell the GAN when we are giving it a certain class. So the discriminator actually has to get good at knowing what's real and what's fake, but not only that, what's a real looking waveform, a signal 1, and what's a real looking signal 2, and so on. So the generator ends up becoming good at generating the signal class that you want. So you feed it in how these classes are represented for these networks so that they can actually be usable. Is we feed them in these vectors. In the case of 3 different types of signals, we use 3 different numbers to signify them. So here we have for the top signal class, we have a 1 in the first index. For signal class 2, we have it in the second, and for signal class 3, we have it in the third. So now this is great. So we have trained a GAN, and we can say, I want 1,000 of signal class 1, 1,000 of signal class 2, 1,000 of signal class 3, and so on. But it's also great because now we have control over the class space, this 3 different numbers here. And we don't just have to ask for any one waveform type. You can ask it for some sort of combination of different waveforms. And what you end up getting out in the end is that you have signals that have features from these 3 different signal classes. So the way I sampled this class space, you can consider it something along the lines of proportions. So in the top here, we have 35% of number 1, 5% number 2, 60% of number 3. And this is what it looks like, according to the GAN. And we can make all sorts of these weird hybrid signals that have a mixture of features. Sometimes you can see one signal dominating. Sometimes if one of these signal classes has too high a strength compared to the others, then predominantly the features of one signal class will emerge. But a lot of the time you get some crazy mixtures of these features that pop up in the one signal. And we can do cool stuff with that. We can interpolate between different classes of signals. So there is an element of randomness associated with GANs, so that it can actually generate very diverse signals within their own class. But if we keep that usually random element the same and just change the class information at the top, we can move from one signal class to the other. So this is originally from number 1, slowly moving 80% number 1, 20% 2. You can kind of think of it in that way. It's probably not exactly like that, but we slowly move from one signal class to the other, and then again from here to another signal class. Now, in the moving from signal class 2 back to 1, there's not too much variation because these two signal classes have a similar shape. But then you can get back to where you started just by moving between these classes. So that's okay. That's a kind of a cool feature, and that's nice if you can make all these mixtures of classes. But what's the point on doing any of that? Why do we need that? Are they even physical? Do we even care? Well, we can try and have a go at using this GAN generated data to train these detection models, which sometimes can give us the wrong answers. And we can try and improve that detection efficiency using this fake data, which we can generate very, very quickly after the training phase. After the training phase, you can generate thousands and thousands of signals in a matter of seconds. So that's useful if you can have a successful training and generate realistic looking samples. So now we don't just only train on the original signals which we had. We can also include in this training of these detection models these crazy waveforms that have features from multiple signal classes. The reason why this might be beneficial is because, especially when these signals are quite hidden in the noise, more of these features might pop out more of the time. And this is one quite focused view on how the detection efficiency can improve. At other times, it isn't quite as good. But by combining these data sets, we can get a performance improvement. What we're looking at here is the signal to noise ratio, the degree of loudness of the signal compared to the blue background noise that we saw in those plots. How big is the amplitude of this orange signal that's embedded in there? And then we can look at efficiency improvement. So this red line is just training on the real data. And then when we include this GAN generated data, we can get some performance improvement, in particular for more quiet signals. And these signals are at a very quiet range compared to what is normally being detected in terms of gravitational waves. But this is to test the model's ability when these signals become very, very much hidden in the noise. So at times, we can get better detection of when those signals are in there compared to when we only train with the real data. So moving on from there, it would be interesting to see how these mixtures of signals might behave when we include more glitch classes or more classes of gravitational waves and so on, and to see if we can further improve upon efficiencies when trying to detect them deep embedded in detector noise. It can be used for other things too, like stress testing some of these anomaly detection algorithms which are being made by giving, maybe they're not so physical, maybe they're not so realistic, but if you fed one of these anomalies to one of these anomaly detection algorithms, you would hope it would find it and it wouldn't consider it just like some normal piece of noise. And that's pretty much all I have to say about the GANs. But if you have any questions, please give me a shout afterwards. Thank you very much.
So today almost come to the end, and I would like to thank all the speakers, and especially Tom's work. If you look at Melissa, they're very different. So with the one way is we use one type of AI techniques, try to find those signals which we think they're abnormal compared with the noises. And what Tom does, actually another approach, which is we consider AI as a human being. We're feeding him some typical example or knowledge that he could tell this AI model start to understand, okay, this is one type of signal which is useful, that's another type, and then slowly the AI model learns on itself. So, and we hope to apply that model and with the fed data to tell us, okay, the things we're detecting in the future, will that be contain useful information? Is there really something hidden in there? And also they could complementary to each other. So his work can apply to the algorithm that Melissa's group is working on to see if their method is really robust enough or not to touch all the edgy cases. So that's a little bit summarized part of our workstream efforts. And I hope you all enjoyed the time. And now let's have a break. And thanks you all for participating for today. Thanks. So any questions and things, feel free to reach the speakers.
We have also some drinks and bites, so it is also some pleasure with it as well.